The title of this talk is Improving Laminar fMRI Specificity by Reducing Macrovascular Bias. Hello. The title of this talk is Improving Laminar fMRI Specificity by Reducing Macrovascular Bias Revealed by Respiration Effects. I have nothing to disclose. First, some background introduction regarding laminar fMRI specificity. We know bold is kind of limited because of joining wing effect and large wings. Usually, we think CBV or CBF-based fMRI have better laminar specificity than bold because there's no joining wing effect. However, those non-bold CBV, CBF-based fMRI may still include the intravascular contribution from large vessels. To resolve this issue, we may be able to use respiration variations in fMRI to reduce signal bias from large vessels. We know that respiration variations will cause significant fMRI signal changes or fluctuations. We usually consider it as artifact or noise source. And there has been a lot of efforts developing different methods to reduce these respiration effects on fMRI. However, respiratory fluctuation pattern in brain could reflect the macrovascular density information, which has been used to improve fMRI specificity in previous research. Here is some study goals. We aim to use the nature respiratory variation in fMRI to improve laminar fMRI specificity. First, we will map the influence of nature respiratory variations at high resolution using 70 fMRI, and we will compare those respiration variation patterns with those from the control breathing task like deep breath and breath hold. And then we will demonstrate the special correlations with large vessel density and utilize those respiration variation revealed information to remove voxels around the large vessels, thereby enhance laminar fMRI specificity. In this study, we will use a MT vapor 3D EPI sequence for both anatomical and functional bold vapor measurement. Vapor is a technique we developed to combine facial and perfusion weighting, so its signal will be sensitive to both CBV and CBF signal changes. All those images were recorded using an identical acquisition so that all analysis, including layer part, can be done in native fMRI space. We acquired data with resolution of 0.8 mm, almost isotropic and almost whole brain coverage. Here is a period of range respiratory curve recorded from a normal fMRI run. The respiration is quite stable generally. However, at some time points, as marked by the red line, there are some subtle respiration changes. Those changes are nature and very small, which the subject themselves did not notice. Based on these respiration variations, we can divide the fMRI time series into two subgroups, with one group of images acquired when the respiration is relatively stable, and the other group of images acquired when there are some small respiration variations. By comparing the difference between the images of those two groups, we can generate a map which we think can reflect the respiration effects. To better understand this map, we ask the questions: how does it compare to the patterns induced by the controlled breathing task like deep breath and breath hold? And can this respiration pattern reflect the large vessel distribution? If it is, it could be very useful for improving layer fMRI specificity. So we did a deep breath experiment for comparison and understanding how respiration affects fMRI signal. First row shows the actual respiration curve. First rest and then take 3 cycles of deep breath and then rest. The image under it represents the actual vapor image acquired during this deep breath period. Bottom highlight the vapor image during rest and deep breath. By comparing them, we can see the signal change most pronounced in voxel around the large vessels as indicated by the red arrows. Here our acquisition is very well aligned with the deep breath phase. In normal fMRI run, the relative timing between acquisition and breath phase could vary a lot. For example, we could acquire fMRI image during breath in or breath out, or in the transition period from breath out to breath in, or opposite. So here we compute the signal change induced by deep breath at a different breath phase, and you can see respiration-related fMRI signal change could be modulated by different breath phase, and actually in different voxels, these breath phase modulation patterns varies a lot, and between also we see a similar respiration phase modulation in vapor and bold. We combine the respiration-induced signal change across different deep breath phase and generate a respiration-related effect-related map as here. And similarly, in nature breath, we compare image acquired during relatively stable respiration and low swing. There are some respiration variations and generate a map. Also, we did a breath hold experiment and generate a respiration effect map. By just visually looking across those maps, we can see the spatial distribution in those three maps are very similar. By a more careful spatial correlation analysis through the cerebral cortex, you can see all those three respiration effect maps are highly correlated. It suggests the respiration map generated from normal fMRI run are similar to those from deep breath and breath hold experiments. Next, we further ask the question, can those respiration variation related fMRI maps suggest the distribution of large vessels? To answer this question, we need a vascular segmentation. Here we used an algorithm developed recently to segment the large vessels based on SWI and QSM images. Then we can do a similar node-wise correlation analysis between large vessel density and the respiration map, and we found they are all still significantly correlated, suggesting respiration effect on fMRI does reflect macrovascular density. In fMRI, we actually don't need any additional data to do this kind of analysis. We can just take advantage of the nature respiration variations to generate these respiration effect related map. Here is an example to use this respiration effect to improve laminar specificity. We conduct a visual experiment acquiring vapor and bold when the subject was watching visual checkboard stimulus. We extract the signal change for bold and vapor across different cortical depths. By removing those voxels most sensitive to the respiration variations, the superficial bias could be significantly reduced, and this is consistent across all individuals. Also, by removing those voxels most sensitive to respiration variations, the signal blurring in fMRI images can be significantly reduced. Here is a summary of the whole talk. Thank you for your interest, and feel free to contact me if you have any questions.